Hi students, Professor Barber here. This lesson is titled One-to-One Functions and Their Inverses. We know that a function evaluates an input value and produces one and only one output value. An inverse function undoes or reverses what that function has done. In this lesson, we learn the requirement necessary for a function to have an inverse. We learn how to compute that inverse, and we learn how to model the concepts of an invertible function in applications. So, upon successful completion of this lesson, you will 1. Be able to identify one-to-one functions. 2. Be able to obtain the inverse of a function. 3. Be able to graph the inverse function. And 4. Be able to solve applications involving inverse functions. Before we get too far in, let's consider this motivating application. Problem. The relative value of currencies fluctuates every day. When the problem was written, 1 Canadian dollar was worth 0.9766 US dollars. Part A, find a function f that gives the US dollar value of f of x Canadian dollars. What this is asking is that if you have, say, x Canadian dollars, and you put it through some function, okay, the output that you get, f of x, needs to be US. So x is Canadian. Put it through the function, and the output is US dollars. The ratio is 0.9766, so this function f of x would be described as 0.9766x. So for x Canadian dollars, you multiply it by a factor of 0.9766, and that gives you the US dollars value. Now let's look at part B. It says use the given information to determine a function g that gives the Canadian dollar value of g of x US dollars. So what part B is asking is that if you have x US dollars, what function g will get us back to Canadian dollars? That is, undo the problem, which means we kind of have to solve for the x. So if you had f of x equals 0.977x, let's just go ahead and write that as y equals 0.9766x. And what we're trying to do is get x by itself. So we would have, let's see, 1 over 0.9766 y, that's what's there, equals x. This time I used a calculator and performed 1 over 0.9766, and that gave me the value of 1.02396y equals x, except the problem said write it in terms of g of x. So we would write this as g of x equals 1.02396x. So these are our exchanges from Canada here to US, and then from US dollars back to Canada. Okay. Now let's just compute part C, f of g of x. So this means we want the f of, and the g of x we computed was 1.02396x. And we are going to compose this or put it into the function for f. So this would be f, which was 0.9766. And then where the x was, we will replace it with 1.02396x. When you multiply the 0.9766 and 1.02396, it comes out to 1. So we find out that f of g of x takes us back to x. This ought to make sense. You get a certain exchange for a Canadian dollar, convert it to US dollars, and then convert it from US back to Canadian. It should be where you started. Let's try for g of f of x. So for the g function, we're going to have g of, and let's see, for f of x, we put in 0.9766x, computed in the g function, so 1.02396, and where the x was, we'll replace it with the f of x function, which was 0.9766x, and when you multiply those two numbers together, you get 1, so we find out that g of f of x equals x. Both of these, f of g and g of f, undid or reversed their operations and got it back to the x. That's kind of the concept behind working with inverse functions. So formally, definition, a function with domain A is called a one-to-one function if no two elements of A have the same image. That is, f of x subscript 1 does not equal f of x subscript 2 whenever x sub 1 does not equal x subscript 2. If f and g are one-to-one functions and f composed with g of x equals g composed with f of x equals x, we say that f and g are inverse functions of each other. And the horizontal line test. A function is one-to-one if and only if no horizontal line intersects the graph more than once. Determine whether the given function is one-to-one. A. F of x equals x cubed. The graph of the cubic function is provided for us. It is an increasing function starting in the third quadrant, increasing up to and intersecting the origin, and then it also increases radically through the first quadrant. Okay, the horizontal line test is what we're going to use to determine if the function is one-to-one. The horizontal line test states that a function is one-to-one if a horizontal line, any horizontal line, does not cross the graph of the function at more than one point. So let's draw one through y equals 4. It intersects at only one point. How about y equals 2? That also. Y equals 0. We'll do the x-axis. Nope. And let's just do one more for good measure. Y equals -3. Nope. All of those horizontal lines we drew, each of them intersects the graph at only one point. Let's do B. F of x equals 2x minus x squared. The graph is an upside-down parabola with x-intercepts at the origin and 2, 0, and it has a vertex at 1, 1. So on this one, let's attempt to draw some more horizontal lines. I'm going to draw one through y equals 1. Ooh, it touches the curve at only one point. It's a tangent, but let's see what happens if we draw horizontal lines lower down the y-axis. For example, at y equals -1. Yep, it intersects at 2 points. Well, how about at y equals -3? Nope, the graph intersects at 2 points also. Since the graph of this function fails the horizontal line test, we say that the function is not one-to-one. Roman numeral 2, the inverse function. For a function to have an inverse or be invertible, the function must be one-to-one. One way to determine whether a function is invertible is from the graph. If the graph passes the horizontal line test, then the function is one-to-one and therefore invertible. Consider the graph of the cubic function f of x equals x cubed. Let's note that this is a one-to-one function. Let's make a t-chart of some of the points of the graph. Label the first column x and the second one f of x. And I'll select the points -2, -1, 0, 1, and 2. for the x values and then compute the f of x values or pull them off the graph. So for -2, I get -8, and then going horizontally across for x equals -1, the y value is -1. For 0, the y value is 0. For x equals 1, the y value is also 1, but for x equals 2, the y value is 8. The ordered pairs -2, -8 and 2, 8 are off the grid, but let's mark the other points on the graph. So that is, let's mark -1, -1, 0, 0, and 1, 1. Okay? Just keep that in mind. So how about the inverse? Well, we get the inverse function by switching the domain and range. That means the x values become the f of x values, and the f of x or the y values become the x values. That's why a function has to be 1-to-1 to be invertible. Anyway, so let's make a t-chart for the points of the inverse function of f. We'll draw a t-chart. Label the first column x. And the second one, I'll just write the words inverse of f. Now we're going to switch the values of the columns. So for the x column, I'm going to write the y values that we got for the original function. So it'll be -8, -1, 0, 1, and 8. And for the inverse of f column, we transfer the corresponding domain values from the function t-chart and write -2, -1, 0, 1, and 2. Let's plot some of these points. So we'll plot the ones we can reach and sort of guess where the other points would be or estimate. And we'll connect these points to see what the second graph looks like. So now we know how to graph the inverse of a function from the graph of a function. Let's observe that the graphs of the inverse functions reflect about the line y equals x. Roman numeral 2, the inverse function. Definition: let f be a 1-to-1 function with domain A and range B. Then its inverse, denoted f, and then superscript -1, has domain B and range A and is defined by f superscript -1 of y equals x if and only if f of x equals y. The inverse function theorem. Let f be a 1-to-1 function with domain A and range B. The inverse function, denoted f superscript -1, satisfies the following cancellation properties. F superscript -1 of f of x equals x for every x in A, and f of f superscript -1 of x equals x for every x in B. Conversely, any function f superscript -1 satisfies these equations is the inverse of f. Let's note, f superscript -1 is read the inverse of f. Find the domain and range of the inverse of f if f is invertible and defined by the following given table. The given table consists of 2 columns and 5 lines. The first column is x, and the inputs are -2, -1, 0, and 2. The second column is f of x, and its entries are -7, 0, 1, and 9. In order to find the domain and range of the inverse, we switch the x and y values. So let's consider the second table for us to complete. the table of values for the inverse function. Everything in the x column for the inverse is going to be what f of x was. So we'll put -7, 0, 1, and 9. And for the f inverse of x, those will be the x values, which is going to be -2, -1, 0, and 2. So to list the domain of f inverse, that will consist of -7, 0, 1, and 9, and the range of the inverse will consist of -2, -1, 0, and 2. Again, for an invertible function, the domain and ranges just switch. Part A. If f of 5 equals 18, find f inverse of 18. For the inverse, the domain and the range switch, so f inverse of 18 will be the input value of the function, which is 5. Part B. If f inverse of 4 equals 2, then find f of 2. Again, for functions and their inverses, the domains and range switch. So for f of 2, that value would be equal to 4. Find the inverse of the following functions if possible. A. F of x equals 5x minus 3. The equation f of x equals 5x minus 3 represents a line. Lines are one-to-one and invertible, so we can find the inverse. To find the inverse, replace the f of x with y and write this equation as y equals f of x minus 3. Now that's my first step. My second step is to interchange x and y. So x is now equal to 5y minus 3. Next step is to solve for y. So x, adding 3 to both sides, would be plus 3 equals 5y. And then divide by 5 on both sides. So x plus 3, quantity, divided by 5 equals y. The final step is to exchange y with the notation f inverse of x. And so your new equation will be f inverse of x is equal to x plus 3 divided by 5. Part B. F of x equals the quantity 5 minus 7x divided by the quantity x plus 2. This is also one-to-one. It is a rational function. So let's see how we would do this. Again, I would begin with 1. Replace the g of x with y. So y equals 5 minus 7x divided by x plus 2. Now switch the x's and y's, so I'll have x is equal to 5 minus 7y divided by y plus 2. The next step then, step 3, is to solve for y. So let's see. I will multiply the denominator of y plus 2 through both sides. So my equation becomes x times y plus 2 equals 5 minus 7y. Remembering that we're trying to isolate the y, so let's distribute the x on the left-hand side first. So x times y, xy, plus x times 2 is 2x equals 5 minus 7y. Let's get all the terms that have a y in it on one side and all of the terms that do not have a y to the other side of the equal sign. I'll begin by adding 7y to both sides. So xy plus 2x plus 7y equals 5. Now let's subtract the 2x from both sides. So xy plus 7y is equal to 5 minus 2x. Again, remember we need the y by itself, so factor out the y on the left-hand side. Then y times x plus 7 remains in quantity equals 5 minus 2x. And finally, we can divide the x plus 7 and isolate the y. So y is now equal to 5 minus 2x divided by the quantity x plus 7. We have one more step remaining, and that final step is to replace the y with the F inverse notation. So let's write the final answer as F inverse of x is equal to, let's see, it was 5 minus 2x divided by x plus 7. For the function f of x equals the square root of x plus 3, A, sketch the graph of f. Okay, to sketch this function, let's begin by getting a couple of points on the graph of this function. So I'll make a t-chart, x in the first column, f of x in the second. It's called a t-chart because I've got the letter t separating it. And I've got to pick some values for x. Okay, I get to choose those. The domain is that under the square root, it cannot be negative, so the smallest x value I could choose is -3, so I'll start with -3. And hopefully, for reasons that become obvious in just a few moments, the next three numbers I'm going to choose are -2, 1, and 6. Now let's evaluate each of those x values in the square root function. So the square root of -3 plus 3, -3 plus 3 is 0, so the square root of 0 is 0. Let's go ahead and plot that on our grid. Okay. Now at -2, square root of -2 plus 3. The -2 plus 3 is 1, and the square root of 1 is just 1. So let's plot the ordered pair -2, 1 on our plane. Let's do at x equals 1. 1 plus 3 is 4. The square root of 4 is 2. Getting why I picked those values? So now have 1, 2. And then let's pick 6. 6 plus 3 is 9. And the square root of 9 is a very nice number 3. So we'll plot the ordered pair 6, 3. Connect the dots. And we get the graph of the square root function shifted left 3 units. By the way, you could have also just graphed it that way. Let's continue. Part B, use the graph of f to sketch the graph of f inverse. You can eyeball it. You can also, let's go ahead and just make a t-chart, but switch the x and y values. So I'm going to make a t-chart for x and f inverse of x. And remember, for the inverse, you just switch the domain and range. So for the x column for the inverse, I'll pick the numbers 0, 1, 2, and 3. And for the output of the inverse function, I'll pick the input values for the original function, which will be -3, -2, 1, and 6. Let's plot those ordered pairs. So we'll do 0, -3, 1, -2, 2, 1, and 3. Oh, 6 is not quite on the grid, but we'll estimate about there and connect the points. And that is the graph of our inverse function. Okay, now part C, find the inverse function f inverse of 1. So to find the inverse, let's rewrite the f of x equals the square root of x plus 3 as y equals the square root of x plus 3. That's step 1. Step 2 is interchange the x and y. Why do we do that? Because the inverse function's domain and range is exactly the opposite of the original function. So we've got x equals the square root of y plus 3. Yep. Now we're going to solve for the y. So to begin this, let's see, we will square both sides. So x squared is equal to y plus 3. And then we've got to solve for the y. So x squared, let's see, minus 3 equals y. So when we make the notational switch, that is replace the y with the f inverse of x notation, you get f inverse of x equals x squared minus 3. But we're actually not done. The reason that we are not done is that the graph of x squared minus 3 is actually a parabola. Shift it down 3 units, and guess what? That's not 1-to-1. That's not invertible. So we have to make the inverse function just as invertible, and the way to do this is to restrict the domain. And for the inverse, we're going to make it so that the domain is from 0 to infinity. Consider the following graphs to answer the questions that follow. We are presented with 9 different graphs, and they are lettered sequentially from A through I. So, which of the graphs, question A, represents y as a function that is always increasing? Always increasing means that as you move from the left to the right, it is always going upwards. The first one in alphabetical order that is always increasing is B. A is not because we have a little resting spot. C is not. D is not. E is not increasing. In fact, the next always increasing graph is the linear function that goes straight through the origin, and that is the graph represented in I. B represents y as a function that is always decreasing. So that means as you move from the left to the right, the value of function is getting lesser. So C is a linear function that's a line that's always decreasing. And that's the only one. Let's look at question C. Which of the graphs does not represent y as a function of x? The test that I use to determine whether or not the graph represents a function is the vertical line test, and all of them except H, which is a graph of an ellipse, represents a function. So H, the graph of the ellipse, is not a function. D represents y as a non-invertible function of x. To be invertible, the graph has to first be a function, and 2, it has to pass the horizontal line test. So looking at each of the graphs, the first graph that fails the horizontal line test because a horizontal line intersects at more than one point is the graph in D. The next one is F. And that's it. The reason that we don't need to write H is because that's an ellipse and it's not even a function. Question number E indicates that y is directly proportional to x. Directly proportional is y equals constant times the x. So that's a line that goes through the origin. So that would be the graph of y. Graph of I, not y. And finally, the last one represents y as a 1-to-1 function of x. 1-to-1 means first it's a function and that a horizontal line does not intersect its graph at more than one point. So A is a function that is 1-to-1. B is a function that is 1-to-1. C is a function that is 1-to-1. D is not. A horizontal line would intersect at more than one point. E is 1-to-1. F is not. You can draw a horizontal line, and in certain parts it could intersect the graph at as many as 3 places. G is 1-to-1. And finally, I is also 1-to-1. The function f of x equals 0.9766x represents the US dollar value of x Canadian dollars at the time this problem was written. The inverse function is f superscript minus 1 of x equals 1.02396x. Part A. What does the inverse function represent? The function itself represents the US dollar value of x Canadian dollars. An inverse function reverses that behavior, that function behavior, so the inverse function represents the Canadian dollar value of x US dollars at the time this problem was written. B. How much Canadian money would $12,250 in U.S. currency be worth? To answer this question, we use the inverse function to solve it, and that's because we want the value of Canadian money with respect to U.S. currency. So in the inverse function, we would use f inverse, which is f superscript minus 1 of 12,250. That is equal to 1.02396 times 12,250, and that product is 12,543.51.